Today we start by talking about scientific notation, which is just an abbreviated form of a number. And the way we write this is we have a number a whose value is an absolute value between 1 and 10, and it's multiplied by 10 raised to a power of any integer. So remember, an integer is all counting numbers including 0. So if we look at our first example, this example is in scientific notation, and they want us to write it as a decimal. So in order to do that, we're going to take and consider the power of 10 right here, which is -4. And when we multiply by a negative power, that means our placeholder is going to move back to the left. So we have 1, 2, 3, 4 places. And in those places where we don't have any terms at all, we just pop in zeros. So we'd be adding 3 zeros to this, and our final number is 0.00062. Likewise, if we're going to write something in scientific notation, we have to take and change this number to a value between 1 and 10, and then a multiple of 10 raised to some power. Right? So again, what we're going to want to do here is we're going to want to make this number look like 5.732. And that's going to be multiplied by 10 to some power. Now, in order to do that, what we really want to do is we're going to have to bring this number back to its original. So if we're here right now and we have to go here to get where we wanted to, then we need to take and, again, just like in the previous problem, move that placeholder back 3 places. So this is going to be times 10 to the -3rd. So these two examples are a little bit different in that you have to do the arithmetic first and then use scientific notation at the end, because in each case, both are in scientific notation to begin with. So if I take 6.23 and multiply it by 2.1, then we know we're going to get 13.083. And that's going to be times 10 to, due to our powers of exponents, we take and add these guys. So that's 10 to the -7. Now in this case, we're going to leave the negative exponents because of scientific notation and not worry about taking the reciprocal. So again, what we're going to need to do is we're going to need to make this a scientific notation number, and a scientific notation number has to be between 1 and 10. This is 13, so this is 1.3083. And then we have to decide what our power of 10 is going to be. Again, this is the original problem, so we have to have a value of 13. And in order to get a value of 13, I'd have to move my decimal place to the right. So that's like multiplying by a positive power of 10 to this. So this would be 10 to the -6th. In this next example, we have a division problem, so we know we're going to have to subtract the powers of 10 when we do that division. But we start by taking 2.8 and dividing by 7.4, and in that case we get 0.3783, and there's a whole bunch of other stuff. I'm just going to leave it right there. All right, and then this is times 10. Again, we're going to have to subtract. -2 minus -8 is -10. Likewise, we have to get our answer in scientific notation. Scientific notation is 3.783 times 10 to some power. Now again, our original would have to get back to here. So we'd have to move to the right, or I'm sorry, that's to the left, 1, and that's in the negative direction, so this is 10 to the -11th. Okay, moving on to simplifying radicals. Now, typically, you're used to just working with square roots probably at this point. But what we're going to do is we're going to expand that a little bit. So, in general, a radical looks like this, where we have this term inside the radical here, and then a term under the radical here. This term inside the radical is called the index. All right, and that tells you basically how many times you need to multiply something by itself in order to pull that number out. We know that square root of 49 is 7. What we haven't really termed too much is that this is an implied 2 in that square root. Now here we have what we call the cubed root of 125. The cube in the index tells us we have to multiply something by itself 3 times to get that number. So when I'm thinking about what multiplies by itself 3 times to get 125, I've got 5. We've got some properties of radicals. Now, if we have an index thrown in here, changes things a little bit. And sometimes we can actually do a problem exactly like this, because we just did one with the cube root of 125. The m was to the first power. However, sometimes it's easier to look at this particular writing of the radical in this form, and this is equivalent. So this is the nth root of a total quantity raised to the m power, because every once in a while these numbers will get huge. All right. Likewise, if I take, and this is a little like properties of exponents, but not quite. The thing about these examples here is that in these two, the indexes are the exact same. So if I have the same indexes and the multiplication of two terms, I can combine that to the product of those two terms under that index. Likewise, if I have a division of two terms with the same index, I can combine that again to the division of those two terms under the same indexed root. In this last example, a little bit different, I have two separate indexes, one contained within the other, and that's equivalent to the multiplication or the product of those two indices, all with the same number under the root. So we'll move on and do some problems. This is something you've probably already done in, 7th, 8th grade. Basically, in order to break these roots down, we're going to look for, in this case, perfect squares within that number of 40. And we're looking for factors. So, in this case, I know 4 is the biggest perfect square, and then I have a multiple of 10 after that. I know the square root of 4 is 2, and I get root 10. Not a real big fan of the tree and branch method, so I just say find the biggest perfect square. In this case here, we can multiply 3 and 5 together because they aren't in roots to get 15, and then we're left with that property that says if I have the same index, I multiply the two numbers underneath and get their product, so that's root 60. That's fine, but it's not finished because I know there's a perfect square in 60. So I have 15, there's a 4 in 60, multiplies by 15, so I get 15 times 2 roots of 15, or 30 roots of 15. Here's a little bit different take on a radical simplification. I've got a integer value here and then a radical value here. Way back in the day, some mathematician decided we would not be looking at radicals in a denominator of a fraction. That wasn't good enough, so we have to simplify it. In order to simplify it, we have to multiply it by a form of 1, because by the identity property, we'll get the same value out that gets rid of this radical here. So what we do is multiply by root 5 over root 5, which is called rationalize. And we're rationalizing the denominator by a form of 1. So that gets us 7 root 5. Root 5 and root 5 is the root of 25, which is 5, and then we're done. So now we look at a case where the fraction's not reduced, and I'm of the inclination to make things smaller before I make them bigger. So I've got 6. I know 3 goes into both those. 24 on top, and I have a 5 in the denominator. I also notice that there's a perfect square in 24, so that goes 6, 4, and a 6 over 5 root 5. That breaks down into 2 coming out, so it's a 12 root 6
over 5 root 5. Again, I'll rationalize a root 5 over root 5, getting me 12 root 30 over 25, and that'll do it.
Now we're going to introduce some variables into this next example. So in this case, what I try to do again is I try to break it down, see if there's any reductions that can happen, and there aren't. But then I try to break down into perfect squares. So in the numerator, I have an x squared and an x in x cubed. In the denominator, I've got a 4 and a 2 for the 8. And then I've got a y to the 6. That's the biggest perfect square there. And a y. I'm going to break that down real quick, simplify it. I've got an x and a root 3x. And then in the denominator, I have a 2, comes out from the 4. And then what multiplied by itself is y to the 6, that's y cubed. Underneath the radical, I've got a 2 and a y. And now I need to rationalize by something that will get rid of this radical here. So that's going to be root 2y and root 2y. So in my numerator now, I have x and the root of 6xy. And in the bottom, I have a root 2 and a root 2, which is a root 4, which is 2, times a 2, which is 4. And then root y, and root y is root y squared. Square root of that is y, so that's y to the 4th. And now we'll move on to perfect cubes. Now in this case, I could multiply this together if I wanted to and get a large number and then try to find out, what's the biggest perfect cube in that number. But in this case, I see that in 16, there is a perfect cube of 8. And that's multiplied by 2. So I'm trying to make it smaller. In 12, there are no perfect cubes, so I'm just going to leave that as the cube root of 12. Simplify to start with, and then that gives me a 2 because the cube root of 8 is 2. And then I still have a cube root of 12, nothing's going on there. Now I can multiply these two together and get a smaller number that's easier to deal with. So in this case, I have 2 cube roots of 24. And I know there's a cube root in 24 of 8, leaving me with a factor of 3 left. Cube root of 8 is 2. 2 times 2 is 4. So that's 4 cube roots of 3. So here are a couple of similar examples with cube roots and variables. And we realize that in this case, since we have fractions, we're going to have to rationalize in the end because you can't have a cube root in a denominator. So in this case, again, I look to simplify if possible, which I can because there's some perfect cubes lying around. I know there's a perfect cube in x to the 4th, so that's 3 x cubed times x. Again, we're cube rooted. And in the denominator, that's 4 y cubed and y squared. And that's in the denominator. So I'll clean that up a little bit. We'll pull out an x here, get a cube root of 3x. And again, I have a y here, a cube root. The 4 is going to stay and the y squared stays. So now I have to get rid of this 4 and this y squared. And I need to find some number that will turn this into a perfect cube and then rationalize by that. Well, I know my first perfect cube that I can think of is an 8. And there happens to be a 4 here. So if I multiply a 2, this product gives me a perfect cube, which is perfect. I then have a y squared, and I need one more y to make that a y cubed so that it's a perfect square. Or I'm sorry, perfect cube. So I'm going to rationalize by the cube root of 2y to both the top and bottom. In this case, I just multiply across. I have x cube roots of 6xy. In the denominator, I notice I have now an 8 on that product, but the cube root of 8 is going to be 2, so I'll bring out a 2. I've got this existing y and then a cube root of y cubed, which is just y, so y times y is y squared. And then that gives me my solution because there's no more reductions to take place. Okay, we move on to the next example, and I'm pretty much going to follow the same attack. I'll see if I have any perfect cubes in any of these two numbers in the numerator and denominator, simplify that down, and then look for a number to rationalize by. In 7, there's nothing, but in x to the 7th, I have x to the 6th as a perfect cube with another x remaining. In 80, I know there's a numerical perfect cube of 8 and 10. Then in y to the 13th, y to the 12th is going to be my biggest perfect cube, and there's a y left. So simplifying that a little bit, I'm going to bring out my perfect cubes. Y squared times itself 3 times gets me y to the 6th. I think I just said y, and it's actually x. So I've got 7 and an x left. Then in the denominator, I've got a 2 that I can pull out. What multiplies by itself 3 times and gets me y to the 12th, that's y to the 4th. And then underneath that radical, I've still got a 10 and a y. So again, I'm going to need a perfect cube to rationalize by to get rid of this. Now I've got one 10 right here. Another 10 is going to get me 100, but 100 is not a perfect cube. So I need 2 more 10s, and 2 more 10s happen to be 100. I'll just do this right underneath so you can see it. So now I've got 3 10s. In the case of y, I need 2 more y's, so I multiply by y squared. And that's what I'm going to rationalize by. So again, we look and I've got a 7 and a 100 to multiply. Neither of those have perfect cubes in them, so my product won't have a perfect cube in it. So I've got x squared. I know that's going to be under the root as well. And a y squared, that's going to be under the root because there's no perfect cubes. So I'm just multiplying together. 700 xy squared. Now we should get some simplification on the bottom. Numerically, I have a 2 here, but I've got this multiplication of 10 and 100, giving me 1,000, which is basically 3 10s multiplying together. So I get to pull out a 10. 10 times 2 is 20. I've got a y and a y squared, which is y cubed, and the cube root of y cubed is y. Tack that onto the y to the 4th, and I've got y to the 5th. That'll do it for today. We'll see you tomorrow.